Hello, good afternoon friends. Let's start our today's GTU paper on dated 24th January 2012. The remaining questions already we were done up to the question 3b. Now let's start with the question number 4a. The next question. Derive the relationship between the line voltage and the phase voltage in the balanced three-phase star connection system. Friends, there are two types of polyphase system, star connection and the delta connection. So here we have to define the relationship between the line and the phase voltage and the current for the star connection. This is simple, the diagram of the star connection and the delta connection. In the figure 1, you can see that the resistance R1, R2 and R3 respectively 20, 30 and the 50 ohms are connected in a star form, whereas in a figure 2 where R12, R23 and R31 is the connection of the delta. So this is the two types of connection, and remember one thing in your mind, whenever you have to just prove the circuit for the star connection or the delta connection, there is a vast difference between the line voltage, phase voltage, line current and phase current in a star and delta connection. So let's see. First of all, just go through some of the terminology which are used in a star and the delta connection. The first one is a phase. Now what is the phase? What is the line? What is the voltage and what is the current? What is the phase? Described by one element or the device in a load, line or the source. It is simply a branch of the circuit. So whatever the branch of your circuit, star or in a delta connection, that is known as a phase. So whatever the voltage respected that phase is known as a phase voltage, and whatever the current passing through that phase is known as a phase current. Now the line. Friends, there are three lines in a star and in a delta connection. So whatever the branches are connected with the transmission line, they are known as a line, where they kept from the source or the destination. They have to applying from the source voltages to that line. Now the neutral is the center point where all the nodes are connected with each other. So the voltage at that point is 0, and this is normally known as denoted by the capital N. Now the phase voltages and the phase current is. The voltages and the currents across through a single branch or individual phase of the circuit is known as the phase voltage and the phase current. The line current. The current flowing through each lines IA, IB and IC is known as the line current. The line voltage. The voltages between two lines are known as a line voltage. Like voltage between line A and B is known as a VAB. The voltage between the line B and C is known as VBC, and the voltages between line C and A is known as VCA. Now just go through one example of the three-phase supply connection in a star and a delta. This is line A. This is called line B, and this is our third line, that is C. So this is a delta type connection where three lines A, B and C. So this is line A. So whatever the current flowing through that line is known as a line current, that is IA. Current flowing through that line is known as IB, and current flowing through that line is known as IC. So this is called line current. Now the voltage is between that line phase A, voltage is between that two lines A and B, that is known as line voltage VAB. Now the voltage is between that two lines B and C is known as VBC, and same here, the voltage between the line A and C is known as VAC. So this is called the line voltage, this is called the line current, and this is for the delta connection. Now this is again the configuration of the star. The star connection is also known as a Y connection because it looks like a symbolic representation of the Y, where all the lines are A, B and C are categorized with the sum of the degree and with the angle. For example, if the A is your reference line, that it is a 0 degree voltage with the 0 degree level, the B is lagging with the A with the 120 degree, and C with lag with the phase A with the again 120. So 120 plus 120, that is 240 voltage, 240 degree. So if you are consider that the C with respect to B, then it is lagging with the 120 degree, but if you are consider C with respect to A, then it is lagging with the 240 degree, and it is seen in the given figure. Now again continue with the star connection. The star connection is formed with the connecting the starting or the terminals of the each phase together. So the starting point of each phase are connecting with each other with the different transmission line A, B and C, and all the ending points of these three lines are connected with each other. That is known as a point N. That is again we can say it's a neutral point. So this kind of configuration is known as a star connection. The line value and the phase value. So for the line and the phase, that is the line voltage and the phase voltage. Now what is the line voltage? The potential difference, that is PD, or you can say that it's a kind of voltage between any two line is known as the line voltage. So in our previous figure, the VAB is our line voltage between the line A and the line B. The phase voltage. The voltage across the two terminals of any one winding is known as a phase voltage. So whatever the phase phase A, so the voltage VA is known as a phase voltage, and the voltage VAB is known as a line voltage. So there is a somehow very small difference between the line voltage and the phase voltage. Now the line current and the phase current. The current flowing through any one line is known as a line current. Like IA is a line current for the transmission line A, IB is a line current for the transmission line B, and IC is a line current for the transmission line C. The phase current, whatever the phase you are considering and the current flowing through that phase is known as a phase current. Generally the line phase voltage and the phase current are the same. Now the star connection. Now see the relationship between the line voltage and the phase voltage for the star connection. Friends, again I am remembering one thing for your mind, that in a star connection or in a delta connection, there is a difference of line voltage, phase voltage, line current and phase current. So first of all, you have to just define whatever the connection you are asked in your exam. Here we are asked in our exam that the star connection. So the line voltage and the relationship between the line voltage and phase voltage is that line voltage is greater than the phase voltage, and it is √3 times higher than the phase voltage. So if you are consider that line voltage is VL and phase voltage that is VPH, so we can say that our VL is √3 times VPH. You can see that VL equals to √3 VPH. Or if you have to find out that VPH equals to line voltage, then you have to write that VPH is 1 by √3 into VL, or you can say that VPH equals to VL by √3. So there is a relationship between the line voltage and the phase voltage in a star connection. Now the next, the relationship between the line current and the phase current for a star connection. Friends, the line, whatever your line current in a star connection, that becomes your phase current. So it means that your IL is your line current and IPH is your phase current. So your IL becomes your IPH in a star connection. So whatever the, for example, if a 5 milliampere is the line current in your star connection, so for your IPH is also becomes the 5 milliampere, because the value of IL and IPH both are same in a star connection. So if you have to find out that IL or IPH, then both are equal. So we can say that IL equals to IPH or IPH equals to IL in star connection. Now the next, whatever the power dissipating in a star connection, there are normally three values we have to just find out: that voltage, current and the power. Power is nothing but the product of the voltage and the current, and this is the AC form and this is a polyphase circuit for the star connection. So our power becomes P equals to, normally the P equals to V into I, but here we have to just taking the analogous value, so we have to just take the P equals to VI cos phi, and this is a three-phase circuit, that's why we have to just multiply by that power with the factor of 3. So we can write that P equals to 3 into power consumed by each phase, that is VPH into IPH into cos phi. Cos phi is denoted that this is a analogous or the continuous value. So for star connection, our VPH equals to 1 by root 3 VL and our IPH equals to IL. So now substitute the value of VPH and IPH into equation of that P. So we can see that the P equals to 3 into 1 by root 3 VL into IL into cos phi. So we can see that you can put that 3 equals to root 3 into root 3. So root 3 is cancel out. So we can write that P equals to root 3 VL into IL cos phi. So this is the power consumed in a star connection. Friends, just go through one video which gives you the simple idea about this star connection, and you have to just find out that how you can convert the star and the delta transformation.
In the previous lesson, we looked at a Y-Y network. Okay, we had a Y source and we had a Y load. Okay, or we had a star source and we had a star load, and we analyzed that network thoroughly. Now we are going to look at a delta connection, or in other words, in this particular scenario we are going to look at a delta connection. Okay, I have a delta source over here. These are my coils which are generating EMF, and this is my load which is connected in a delta network. Okay, I am assuming that I have balanced loads. So this is Z angle phi, this is Z angle phi, this is Z angle phi. Okay, these are my transmission lines. Okay, and my load is connected by simply joining this to my transmission lines. Okay, now I have a delta connection which I would like to analyze for line and phase quantities. Okay, what is your line voltage? Your line voltage is voltage across your transmission lines. Okay, so it is this voltage which is same as the voltage between this point and this point. Okay, so essentially your line voltage is the voltage in your coil. Okay, let's just say my coil voltage is Vm angle 0. My coil voltage in this particular coil is Vm angle minus 120, and in this particular coil it is Vm angle minus 240. Okay, so my line voltage VAB is Vm angle 0. Okay, what is your line voltage VBC? Your line voltage VBC is simply voltage across this point and across this point, which is this voltage. Okay, and what is your line voltage VCA? It is the voltage across this point and this point, which is the voltage generated in this coil. Okay, so I have got my line voltages. Now let's look at what is phase voltage. Okay, your phase voltage is voltage across this element. Okay, voltage across this element is simply voltage across this point and this point, right, which is same as voltage across this point and this point, which is same as this voltage. Okay, so in a delta connection your line voltage is same as your phase voltage. Okay, so basically I can write that my VAB is equal to Vm angle 0, my VBC is equal to Vm angle minus 120. My VBC is between this point and between this point. Okay, so it is Vm angle minus 120, and my VCA is between this point, which is my point C, which is this guy, and between this point, which is this point. Okay, so it is Vm angle minus 240. Okay, so VCA is equal to Vm angle minus 240.
Question 4b. Prove that for the pure inductive circuit, for the single phase, current lags behind the applied voltage by 90 degree. Friends, generally we see that the circuit is made from the component resistor, inductor and the capacitor. So pure inductive circuit, it means that the circuit which doesn't have the two other components like a resistor or capacitor. There is no circuit in a wall that doesn't have any resistive component. But if you are made from the copper with the iron with the very solid area, then somehow you can reduce the resistive parts. So practically the pure inductive circuit is not possible, but the theoretically we just see that the circuit which have only the inductor in a main component is a main component, then it's known as a inductive circuit. So we have to just find out that in our inductive circuit the current is lagged with the voltage by the 90 degree. So how it is possible? Now just we go through. This is known as this is called the pure inductive circuit, where you can see that at the right hand side the one bar contains only the inductor components, no other elements in this circuit. That's why it is known as a pure inductive circuit. The source induced EMF is known as a V of t equals to Vm sin omega t. It means that it is a sinusoidal component which is a alternating quantity, or it is a analogous quantity. IR is a current flowing through that coil. The voltage is, whatever the voltages are generated in that coil is known as a VL. VL is the induced